Let's do problem 4 from homework 8, which is from the spring 2018 midterm 2 exam. It was question 2 on that exam. So we have this RC circuit, which I've drawn over here. And initially the switch is open and the capacitor is uncharged, Q equals 0. At some point, the switch is closed, and we want to know what is the current through R1, the instant after the switch closes. So one thing I'm going to do to this diagram before we do anything else is I'm going to take this little point on the circuit, and I'm going to label it point C, not to be confused with capacitance, but then I can refer to VCB as the voltage across that capacitor. Okay, so the instant after, we're going to say at time, at t equals 0, the switch is closed. Well, we close it. At t equals 0, close, switch, S1. Now, remember, when you say open and close for a switch, it's like the way a door looks. It's not the way a door functions. So when we close the switch, that means that we do this. So this switch that was open, now the switch is closed. So a closed switch allows current to flow. An open switch prevents the flow of current. Okay, so at time 0, we close the switch S1, and we want to know what is the current through R1. So I'm going to label this current I1, and then I'm going to label this current I2, and I might as well label this current I3. Okay, and we know Mr. Kirchhoff, the current rule would, the junction rule would tell us that I1 equals I2 plus I3, because the sum of everything going into junction A, which is I1, must equal the sum of everything going out of junction A, which is I2 plus I3. But we digress. So at t equals 0, we have, here's, I'm going to call this plus Q, and here's minus Q. So that's the charge on the capacitor. So at t equals 0, Q equals 0. And so an instant after t equals 0, Q is still 0. It's only infinitesimally different from 0. So that means that we can treat this capacitor, which has 0 charge on it, as if it were a wire. So that's really convenient. There's 0 voltage drop. So that means Q equals 0. So that means VCB. That's like this point minus this point equals 0. So then that means that I3 R3, that's the voltage drop across resistor R3, is the same as I2 R2 at t equals, I'm going to say t equals 0 plus, that's like an instant after we close the switch. So that means like R2 and R3 are in parallel, because this capacitor is basically like a wire at that instant when it has no charge on it. So then we could write the loop rule, but the simplest way to figure out this current I1 is that we have R1 in series with the parallel combination of R2 and R3. And again, the reason we're able to do that, we know the top sides of R2 and R3 are connected together. For them to be truly in parallel, their bottom sides also have to be connected together. But when the capacitor has 0 charge on it, effectively they are connected together because this voltage, VCB, is 0. So then we can say, we could just write down directly, like the previous video, I was a little more step by step, but in this video I'm just going to write down directly Actually, I don't want you to see that yet, so I'll leave the problem there. I'm going to write down directly that I1 equals this battery EMF divided by, and then it's just the equivalent resistance here. So it's R1 plus then the parallel combination of R2 and R3. So that's 1 over R2 plus 1 over R3 reciprocal of. Or you could replace this thing in parentheses. Well, you could also say this is the battery EMF divided by R1 plus, here's R2, R3 over R2 plus R3. Just be careful not to do this if you have 3 or 4 resistors. It only works with 2. So I guess we can just evaluate that. Oh, we need numbers. So the battery EMF is 80 volts. So here's 80 volts. And then R1 is 60 ohms, and R2 is 60 ohms, and R3 is 20 ohms, and then this capacitance is 25 microfarads. Okay, so 80 volts divided by, so then this denominator is going to be 60 ohms plus, and now the parallel combination of 20 and 60. So 20 times 60 is 600, 1200. 1200 divided by 80 is 120 divided by 8 is 15. So this is 60 ohms plus 15 ohms is 75 ohms. So there we go. 80 volts divided by 75 ohms. And I guess we can evaluate that numerically too. So 80 over 75 is 1.0667. Okay, so this is 1.0667 amps. I like to keep 1 or 2 extra digits for intermediate results, but I guess this is a final answer for this part of the problem, so it'll be 1.07 amps to answer this part of the problem. Then we can go on to part B. So that was part A. What is the current through R1 the instant after the switch closes? There we go. 1.067. Yeah, and my solution said 1.07 amps. What is VA minus VB the instant after the switch closes? Okay, so that's basically, to answer that, we have to know I2. Well, actually there are 2 ways we could do that. Let's do it both ways. One way is we could figure out I2, and then we know VAB equals I2 R2. That's actually more complicated. Let's do it the easy way first. So we can use the loop rule for this loop. So we go up through the battery, to the right through R1, down through R2, and then we're back where we started. And so then that's going to say, with the loop rule, EMF minus I1 R1 minus I2 R2 equals 0. We're back where we started. But notice I2 R2 is exactly the quantity we're looking for. That is I2 R2 I2R2 equals VAB. VAB is a shortcut way for writing VA minus VB. So this says the battery EMF minus I1 R1, that equals I2 R2, just moves this to the other side of the equation, and I2 R2 is precisely this quantity we're looking for, which is actually easier to write VAB instead of VA minus VB, but this gives the sign convention explicitly. Okay, so we already figured what I1 is, so This is 80 volts minus 1.0667 amps times 60 ohms. And I think the answer is going to be 16 volts, but let's just do this again. So here is 80 minus that I1 times 60, and you get 16 volts. Okay. I think this is really the right way to solve part B here. We could just use the loop rule, and we notice that I2, R2 is exactly the quantity we're looking for. If you really wanted to find I2, you can notice, I don't recommend this because, you know, time is always kind of like precious on an exam. But if you want a digression, let's see if we can figure out what I2 is kind of directly. So the junction rule at point A tells us that I1 equals I2 plus I3. Okay, so basically the current coming into point A gets split up into two paths, two parallel paths. And now there's something special about this instant we're looking at, where it's just an instant after we closed the switch. Oh, you know what? There are parts of what I've been writing that you can't see, so I'm gonna do this. Sorry. Okay. So there, at this instant, that capacitor is still behaving like a wire because it has no charge on it. So if you have two purely resistive paths, then the two paths divide up in proportion to their reciprocal resistances. So, you know, I2 plus I3 add up to I1, and then you know, see, the path R2 is 3 times as big as R3. So you know that the current through I3 is going to be 3 times as big as I2. So you actually know that I3 is going to equal 3I2 because the current, if it's just a purely resistive path and there are multiple paths, the current is going to flow in proportion to the reciprocal resistance. You could say that more explicitly by saying that I2 is, what fraction of I1 is I2? So here's I1 times, so it's going to get a fraction 1 over R2. It's a weighted average, so the two weights are 1 over R2 for path 2 and 1 over R3 for path 3. So this is I1. See, 1 over R2 is, oh, okay, so this is like 1 over 60. And then I'm going to just cancel out the ohms. The ohms cancel anyway. And then this is 1 over 60 plus 1 over 20. And so then if you do that math, then you get I2 must be, see, it's a 3-to-1 ratio. So I2 must be 1/4 of I1. So if we actually worked this out, this would be the same as 1/4 of I1. Okay, I couldn't resist checking. This does indeed work out to 1/4 of I1. So then that means I2, 1/4 of this 1.0667 amps is 0.2667 amps. And then I2 R2, so you multiply this now by 60 ohms, and you get 16 volts. Okay, so you see, you could do it that way, but that's actually longer than simply writing down the loop rule here and noticing that this term is exactly the expression you're looking for. Okay, so there you go. So we got part B is 16 volts. Let's see what we want to do for part C. So part C, after a very long time, the charge on the capacitor no longer increases. It has reached its asymptotic value. What is VA minus VB at that time? Okay, so here's where the diagram I have hiding behind the figure is sort of useful. So, like when we flip a switch in these RC circuit problems, it always turns out, I haven't thought of a counterexample yet, it always turns out that some current, some charge then starts moving one way or another. So the current, which is charging or discharging the capacitor, starts out at its maximum value. And the maximum value is like the circumstance that the charge on the capacitor immediately after the switch is flipped for a circuit that has both resistors and capacitors is the same as the charge on the capacitor immediately before the switch was flipped. And then it has this exponential form. So it's like I0 times e to the minus t divided by tau, the time constant tau. And then so there are two tricks then. I mean, two things you have to do. You have to figure out what is this current at that first instant, and you have to figure out what is the time constant. And the time constant is like some product of R times C, but sometimes the R or the C requires combining several components together. So let's work that out. Okay, so we want to know, well, actually, we're going to really work that out for part E, I guess. So for part C, after a very long time, the charge in the capacitor no longer increases. So you see, is that this that's why we're looking at this graph. It's at this asymptotic value here. So the current is 0. The charge is stable. So then what does that do to let us figure out VA minus VB? So at that time, a long time after the switch was closed, this Q, so we have now dQ dt becomes 0 after a long time. So then that means that I3 equals 0 because I3 equals dQ by dt. So this charge has stabilized on the capacitor. So this I3 is 0. So if I3 is 0, then at that very long time after we close the switch, then I2 equals I1. And that makes this circuit then easy to analyze. So then we know that I1 is just going to be the battery voltage, the battery EMF, divided by the quantity R1 plus R2. So let's work that out. Okay, so this equation is still good, but I2 equals I1. So this equation becomes a lot easier. It's battery voltage minus I1 R1 minus I1 R2 equals 0. So we get the result that maybe you would have written down without doing any computation, which is that I1, after a long time since we closed switch S1, just equals the battery EMF divided by R1 plus R2, which is 80 volts divided by 60 plus 60 is 120 ohms, which is 2/3 of an amp. So that is 0.6667 amps. But we really want to know what VAB is. So once again, like, see, we could just rearrange this. We know this thing in the box equals VAB. So we could say EMF minus I1 R1 equals I2 R2. That's actually, yeah, that is the same thing as VAB, the voltage drop across R2. So we could evaluate this voltage we want by either evaluating the right-hand side or evaluating the left-hand side. Let's do both. So if we evaluate the left-hand side, this is 80 volts minus 2/3. Yeah, it's really like, it's 2/3 of an amp times, and then R1 is 60 ohms, okay? and I'll just keep writing it up here. So that's 40 minus 2/3 of 60. 2/3 of 60 is 80 minus 2/3 of 60. 2/3 of 60 is 40. That's 80 minus 40. That's 40 volts. Okay. Or we could evaluate the right-hand side here, I2, R2. So I2, R2, at this very long time after we close the switch, is the same as I1, R2. And that is, again, 2/3 of an amp times 60 ohms. So that also is 40, that's 40 volts. Okay, so that makes sense. So either way, VAB is 40 volts. By the way, there's even one more way to see that. Here's a digression. You see, I can digress if we're on video, because you can always just tune out the parts you don't like. So if you have a circuit where all of the current flows through one resistor, and then all of that current flows through this second resistor, and there's no other path, like here. Here's a battery, and then here is R1, and then here is R2, and you want to know what is, here, I'll call this point C. Here's this point B, this is point C. No, this is point A. Sorry, this is point A, this is point B. Okay, so then you want to know what is VAB. So here's this current, I. So VAB actually equals I R2, and you know that I is the battery EMF divided by R1 plus R2. So this just equals the battery EMF times R2 over R1 plus R2. So you see, it's a fraction of the battery EMF. So each of these two resistors gets a proportion of the battery EMF, which is in direct proportion to its own resistance. So the voltage across R2 is R2 over R1 plus R2. And then, of course, the voltage across R1 is R1 over R1 plus R2. So that's called a voltage divider, this little circuit fragment. That's a little digression I can do in video form. So in this particular case, R1 and R2 are the same, so the result is just 60 divided by 120. It's 1/2. So it's 1/2 of the battery voltage. So that makes sense then that it's 40 volts. So if you happen to know that all the current going through R1 continues through R2, and if you happen to have in your head what a voltage divider does, and you happen to notice that these two resistors are the same, then it could make intuitive sense that VAB is 1/2 of the battery voltage in this case, where you've kind of reduced the circuit to a voltage divider because I3 has become 0 at that time, a long time after the switch was closed. One way or another, the answer is, after a very long time of S1 switch being closed, the voltage VAB across resistor R2 is 40 volts. And then I think it's going to turn out for the next part of the problem, we want to know what is the voltage across the capacitor at that same very long time, because we're about to flip the switch back, and our starting point after we flip the switch, the capacitor has the same charge the instant after we flip the switch as the capacitor had the instant before we flipped the switch. That's true in RC circuit problems. So I might as well discuss while we're here. Notice that if I3 is 0, then there's no voltage drop across this resistor. So if I3 equals 0, that means that I3 R3 equals 0. So that actually means that VAC is 0. You see, that's the voltage between point A and point C. That's 0. So so the voltage between points A and B is the same as the voltage between points A and C plus the voltage between points C and B. You see? So like this voltage difference between A and B must equal this voltage difference between A and C plus this voltage difference between B and C. That's like saying VA minus VB equals VA minus VC plus VC minus VB. VA minus VB equals VA minus VC plus VC minus VB. But because there's no current flowing through R3, so VAC is I3R3. So that is 0. So therefore, VAB equals VCB. You see, so the voltage, and then VCB is just Q over C. That's the charge on the capacitor divided by the capacitance. So at this time, a long time after the switch has been closed, the voltage across the capacitor is the same thing as this, like I2 R2. So VAB, the voltage between here and here, is just I2 R2. The voltage, that's the same as the voltage between here and here, but because there's no voltage drop across R3, that's also the same as the voltage between here and here across the capacitor, because there's no IR drop across this resistor, because there's no current here, because this charge is constant. So that's super convenient. So that means that we know that, like, the initial charge, well, not the initial charge, the charge after a long time on this capacitor is just this capacitance of the capacitor times 40 volts, which is the battery EMF over 2. This is like after S1 closed a very long time. Okay, or so then the voltage across that capacitor is going to be 40 volts. So we're going to use that in part D of the problem, asking what's happening just after the switch is opened. Let me erase and we'll do that. Okay, so we had found that after switch 1 had been closed a very long time, VAB was 1/2 of the battery EMF. So that's 1/2 of 80 volts, so that was 40 volts. And then because I3 was 0, which we needed to work this out anyway, then that also equals the voltage across the capacitor. So Q over C, the voltage from this plate, top plate, to the bottom plate of the capacitor, is also 1/2 the battery EMF, because there's no IR drop across R3. So now we're going to open S1. So here we go. We're going to open S1, and now it looks like that. And so now this is 0. And in fact, I think we want to redraw all of these currents. We want to know what is this voltage now across R2 in this new scenario where essentially this left half of the circuit is really no longer there, right? Because there's no current flowing over here. So we might as well erase it. So this is all that's left because we opened that switch. So now we want to figure out what direction the current flows. So we know what the initial charge on the capacitor is. The charge on this capacitor immediately after we open the switch is the same as the charge on that capacitor immediately before we close the switch. And so then what's going to happen? So it seems like this is plus, this is minus. So now the current is going to flow like this, up through R3, down through R2. So we could write a loop rule which says, so we'll start with the capacitor, and it's got some charge separated here, so it's kind of like a battery, except that its voltage isn't constant, because as we move charge out, the voltage goes down. But this is Q over C for the capacitor, minus IR3, because the way we labeled our current is going up through R3 and down through R2, minus IR2, and then we're back where we started. That equals 0. So then this current I is the voltage on the capacitor, which I just wrote as Q over C. So here's Q over C. We don't really need to know what Q is. I wrote it this way because you want to bear in mind that what's really, like, the reason why this is true is because that charge Q hasn't had time to go anywhere yet. So there's Q over C divided by R2 plus R3. There's volts divided by ohms is going to be amps. Okay, so this Q over C, its initial value, so this is like, this is going to be like immediately after opening the switch is going to equal, this is the battery voltage over 2. And then the sum of these two resistances is 80 ohms. So that's 40 volts over 80 ohms. So that is a half amp, 0.500 amps to our standard 3 significant figures. So that was, oh, that's not the answer yet, sorry. That's what we need to get the answer. Now, VAB, that's like VA minus VB. VAB is just IR2, and so that must be a half amp times 60 ohms, so that is 30 volts. Okay, so that's the answer we're looking for. So now you see the instant after we reopen that switch so that current no longer flows through the battery, now the voltage between A and B is 30 volts. So point A is 30 volts higher than point B. And the current is still flowing down through R2, but what's different is the current is now flowing up through R3 instead of flowing, well, initially the current was flowing down through R3 to charge the capacitor, then after a very long time the current through R3 became 0 because the capacitor had reached its asymptotic charge, and now we disconnect the battery, so now charge is flowing out of the capacitor, so current is flowing back up through R3. Then part E, how long after the switch is opened will it be until VAB is 10 volts? Okay, that's why I left this diagram here from an earlier problem. So we can write that this current is the current immediately after we open the switch times e to the minus t over time constant. What is the time constant? The time constant, so you want to think, it's not like every resistor and every capacitor in the problem necessarily. You want to think like, what's the path, like, how many capacitors are charging or discharging, and what's the current path? So there's only one capacitor here, but that current has to flow through these two resistors in series. So this is the equivalent resistance of those two resistors in series, which is R2 plus R3 for series combination. And then there's only one capacitor. So that is 80 ohms times 25 microfarads. So that would be like 250 times 8. That's like 250 times 4 times 2. That's 1,000 times 2. So this is 2,000 microseconds. So that's 2 milliseconds. It's actually, you could say 2.000 milliseconds. So there's 2 milliseconds is our time constant. So now this is, we want to know when. Okay, so let's figure out what that time is. So this is a half amp times e to the minus t over 2 milliseconds. And we, sorry, this is I. Okay. So then VAB, maybe I shouldn't have written in numbers yet. Okay. So VAB is IR2. So then that's I0 R2 e to the minus t over time constant. And this, we want this to equal 10 volts. So then that says 10 volts divided by I0 R2 is e to the minus t over time constant. And then that implies that the logarithm of 10 volts over I0 R2, that's a half amp times 60 ohms. So this, I guess this is that same number, 30 volts. 10 volts over 30 volts equals minus t over time constant. We could do one more intermediate step, and that means that the logarithm of 30 volts over 10 volts is plus t over time constant, because you change the sign of the logarithm. You negate the logarithm, that just takes the reciprocal of the argument of the logarithm. So that means that the time that we want is this time constant times the natural log of 3. And the time constant, we said, was 2 milliseconds. So there we go. So the answer is going to be t equals 2 milliseconds times the natural log of 3, which I think is going to be like 2.2 milliseconds. So let's ask Python. 2 times the logarithm of 3 is 2.197. Okay, so 2.20. That is 2.20 milliseconds, not microseconds, but now milliseconds. So that is, yeah, there's part E. So that's the end of that problem. So I think these RC circuit problems are pretty tricky, but there's a few things to bear in mind. When a capacitor is fully discharged, it's like a wire. When after a very long time the charge on the capacitor has stabilized, that means the current through that capacitor is 0 if the charge on that capacitor is constant, because the current is the rate of change of the charge on that capacitor. And for these RC circuit problems, the state of the capacitor immediately after you throw a switch is the same as the state on the capacitor immediately before you throw the switch. So that's usually the trick involved, is you figure out what the state of the capacitor just before you threw the switch, and then the capacitor, because of this finite time constant, the capacitor charge can't change instantly. It takes some time to change. So the charge on the capacitor, like the very instant after you throw the switch, is the same as the charge on the capacitor the very instant before you throw the switch. Okay.